Let me solve this equation by an unusual method. See, I think that my way is very good. I will share with you. Now, I know that x must be a complex number, which is a plus bi. Then I consider this is a z1. So z1 is x plus 3, which is equal to a plus 3, right, plus bi. Yeah. And z1 modulus is equal to square root a plus 3 square plus bi, b square. And the argument of z1 is equal to arctangent b over a plus 3. Yeah, that's correct. And consider this is z2. z2 is x plus 1, which is equal to a plus 1 plus bi. Then the modulus of z2 is square root a plus 1 square plus bi, b square. And the argument of z2 is equal to b over a plus 1. Good. So far, so good. Now, this is equal to z fourth, right? z1 fourth power, which is equal to a plus 3 plus bi to the fourth. And z2 fourth is equal to a plus 1 plus bi to the fourth. Yeah. Okay. Now, the key step is this. The key step is that this plus this, this plus this, this plus this is 16. No imaginary part. Therefore, z1 fourth, z2 fourth must be symmetrical with respect to real axis. Why? Because their sum is 16. There's no imaginary part. So it must be symmetrical with respect to real number. See, this equal to that. The sum has no imaginary part. They cannot be like this. z1 fourth, z2 fourth, like this. The sum, the real number sum is a 0. It's not possible. This, the sum of this, the sum of their real part is negative. This is not good. Well, will be, she just, this will be this possible. This is z1 fourth. This is z2 fourth. Now the imaginary part, same. Therefore, the sum is a 0 imaginary part. And this minus that is 16. Will that be possible? This minus this plus this rather, 16. This cancel out. Will that be possible? Well, I'll leave it for you to consider. See, I think this is unlikely. See, so basically this is the case, right? Or vice versa. Z2 is there, Z1 is there. Does it not affect our analyzation? So one way or the other, the important thing is that this angle must be equal to negative of that angle. That is my conclusion. See, that means this argument, which is an argument of z1/4 must be equal to negative argument of a z2/4. That is what I want to conclude. See, this one, that one, the angle must be negative each other. Now, by the Moivre theorem, argument of this, by the Moivre theorem, argument of this is equal to 4 argument over z1. Right? This is equal to negative 4 argument over z2 by the Moivre theorem. So, which means this one is equal to that. Arctangent, this equal to this must be them, right? Now, I missed to write this one. This is, sorry for that. This is arctangent, B over A1. Well, this is this, not this. So, they must be negative each other, right? So this one equal to negative that. Therefore, B over A plus 3 is equal to negative B over A plus 1. That is what I want to conclude. This is a key step. So this one has two possibilities, that B equal to 0 or B not equal to 0. B could be 0. And B could not be, B could not 0. Therefore, you have different cases to discuss. If B equal to 0, then A must be something, right? If B is not 0, then B can be cancelled out. So this means A plus 3 is equal to negative A plus 1 if B is not 0. So from which that A equal to negative 2. Yeah. So we have two cases to discuss. One case is that X is just a real number, no imaginary. And the other one is that X equal negative 2 plus BI. Yeah. Okay, let's discuss B equal to 0. Yeah, B equal to 0. If B equal to 0, which means this plus this is 16, which means that B equal to 0, this is A plus 3/4 plus A plus 1/4 is equal to 16. Right? If B equal to 0. 16 is a true form. Right? So we have two cases. This equal to 0. This equal to 0, then A equal to negative 1. Right? Negative 1, this 2. Yeah, perfect. If the other one is that A equal to negative 3, this equal to 0, then this equal to 2. 2 to the 4th is still okay. So A equal to negative 3. Yeah, that's correct. Therefore, we have two solutions. X1 is equal to -1. B is 0, right? Bi is 0. The other one, X2, is a negative. So we find two solutions. Then the other case, B is not 0. B is not 0. B is not 0. We know that A must be -2. So, right? So X is equal to -2 plus Bi. So that's the case. Then we go back to this again. This plus this is 16, in which B is not 0, A is -2. So, which means that A is -2. So 1 plus Bi to the fourth plus this, -1 plus Bi to the fourth is 16. Wow, it's good. Let's just square this one first. This is 1 minus B square, right? Plus 2Bi square, yeah. Plus this is square. This is equal to 1 minus B square minus 2Bi another square, yeah, equal to 16. Now this time we square again, but we consider the real part only because this has no imaginary part. We consider the real part only. The real part will be 1 minus B square minus 4B square. Right? That's the real part after after squaring. Same thing as this one, 1 minus B square minus 4B square equal to 16. Yeah, and forget imaginary part. And this means that these two are the same. 1 minus B square minus 4B square is equal to 8. Yeah, this is good. This means that 1 plus 1 plus B fourth, right? Minus 2B square minus 4B square equal to 8. So simple equations. B fourth minus 6B square minus 7 equals 0. Yeah, that one's easy. This is B square minus 7, right? B square plus 1 equal to 0. Yeah, very good. So we have a B square equal to 7 or B square equal to -1. Okay. Now, B is a real number. Therefore, B squared cannot be -1. So left only this, right? So B is a plus or minus √7. Wow, we found a B. We found a B. And A is a -2, right? So X3 is a -2 plus √7i. X4 plus is equal to -2 minus √7i. Yeah, that's good. So plus the previous solutions. So x1 equal to this one, x2 is a -3. So altogether, we have 4 solutions. See, I think that this method is very good. I haven't seen anybody did it. So, oh, by the way, I have another video discuss almost the same, similar to this kind of equations, using almost a similar questions, similar solutions, similar method. Now you can go see. Well, I think they're very good methods. Nobody has done it. Thank you.